Greetings, folks. Welcome. The practice of statistical inference involves using information from a sample of data to say something about a larger population. For example, you might want to test a claim you have about a population mean or proportion. So here's a claim I have about a population proportion. It's that I think that more than 60% of all college students hum along to Taylor Swift songs. Of course, I would never have access to every single college student, so instead I try to test this claim doing statistical inference, that is, taking information from a sample to say something about that larger population. So the first step in this hypothesis test is to write out the hypotheses, and as usual, the claim is written out as the alternative hypothesis. So here you see the alternative hypothesis, which is H subscript A, is P, where that's the proportion of all college students, is greater than 0.60 or greater than 60%. And I'm going to test that against the null hypothesis, which is written as H subscript 0, and that's where this P, again, the percentage of all college students, is less than or equal to 0.60. The second step of a hypothesis test is to set your significance level, which is alpha. For this particular test, I'm going to use a significance level of 0.10, and that's a decision I make as a researcher where I'm willing to tolerate a 10% chance or 10% probability of making a type 1 error, which is rejecting the null when in fact the null is true. So now the third step is the fun part where you actually get to conduct your research. So let's say I did a survey of 30 college students and I asked them whether or not they sing along to Taylor Swift. And let's say that 21 of those 30 students said in fact that they do sing along when a Taylor Swift song comes onto the radio. And that's 0.70 or 70%. So again, that's information from my sample. So we use information from that sample to calculate the test statistic. And since this is a hypothesis test about a proportion, the test statistic is a z-statistic. And here you see the formula. It's P bar, again, this is this proportion from our research, minus P subscript naught, which is the proportion from the null hypothesis. You divide that by the square root of P subscript naught times 1 minus P subscript naught, and you divide that by the sample size, and then again, you take the square root of that whole bit. So now we can take the data that we collected from our random sample of 30 students and calculate the test statistic. Again, this is the statistic. It's 0.7, again, this is the sample proportion from my research, minus 0.6, that's the proportion from the null hypothesis. You divide that by the square root of 0.6 times 1 minus 0.6, and you divide that by 30. So you end up with a z-statistic of 1.12. And your intuition should tell you that really this z-statistic is not very large. Typically, if you have a large z-statistic, or if you're doing a hypothesis test about a mean, if you have a large t-statistic, you're more likely to be able to reject the null. So in this case, we're thinking, this sample proportion of 0.7, it's only 1.12 standard errors away from the proportion of the null hypothesis. So again, we're thinking, our intuition is already telling us that we're not going to be able to reject the null, but still we want to continue on with this problem just to see for sure. So to find the p-value, we need to find the percentage of the distribution that corresponds with a z-score of 1.12. So here you have a standard normal curve, which has a mean of 0 and a standard deviation of 1. And I put in the z of 1.12. And again, the question is what percentage of this distribution corresponds with a z of 1.12. So we can go to our handy standard normal table. And if you remember, the standard normal table shows cumulative values. So you go down that left column, you see a z-score of 1, 1.1, 1.2, 1.3, etc. If you go across the top, you see 0, 0.01, 0.02. So you find the z-score of 1.12 happens to be 0.8686. Again, that tells us the cumulative part of the distribution that goes up to a z-score of 1.12. So if 0.8686 of this standard normal distribution is to the left of a z-score of 1.12, That means to the right of the z-score of 1.12, you have just over 13% of the distribution, or more precisely, 0.1314. So now we can use that value from the standard normal table to find our p-value of 0.1314. You might remember that the p-value is the strength of the evidence for the null hypothesis, and this p-value of 0.1314 is not huge, but it's still large enough that there's reasonably strong evidence in favor of the null hypothesis. In other words, and again, we anticipated this earlier, our claim is probably not true. So then the final step is to compare the p-value to the alpha that we set. Again, we set an alpha of 0.10, which means we're willing to tolerate a 10% chance of rejecting the null hypothesis when it's true. With a p-value from our problem of 0.1314, that tells us there's about a 13% chance that if the null hypothesis was true, we could get a test statistic of that z of 1.12 or higher. So now, since that p-value is greater than the alpha that we set, we cannot reject the null hypothesis in favor of our claim. In other words, we cannot say that with a 10% significance and based on a sample of 30 people, more than 60% of college students sing along when they hear a Taylor Swift song on the radio.